Hi, everyone, and good afternoon from London. I'm Francois from University College London, and today I'm going to talk to you about sustaining renewable resources under uncertainty. So the starting point of this project was really to consider sustainable development goals and to try and figure out how some of those goals actually align and emphasize the need for proper sustainable resource and renewable resource management. So the SDGs Sustainable Development Goals were adopted in 2015, but they were a long time in the making, and you can trace them back to the Rio Earth Summit from 1993. So there are 17 goals in total, but I'd like to focus the discussion today in this talk on two particular goals, which are goal number 8, which is decent work and economic growth, and another goal, which is goal number 13, which is climate action. So those two goals really frame the issue around the management of renewable resources, and in particular exploitation, which is linked to some extent to economic growth, but also access to food and non-scarcity of food, and regeneration on the other hand, which is itself linked more to climate action. So the take-home message of this presentation, this is all you should remember from it, is that randomness matters, uncertainty matters, and strategic behavior, so also called game theory, matters. So effective management of renewable resources requires taking all those three aspects into account. And so the presentation today is a very basic framework which basically does that and looks at those three different behaviors and put them together. So in the usual setup, we will suppose that we've got a resource R, and we consider its size. And so this is typically the case for forest, for fish populations, endangered species, and so on. And it's traditionally modeled as a ordinary differential equation. So we've got drdt is equal to the difference between two functions, f and h. And so f is the so-called degradation regeneration function of the resource, right? So it typically measures sort of naturally the renewal of the stock of the resource. And h, on the other hand, is the harvest function. I will usually assume that it is the human harvest function, typically fishing, for instance, or tree falling and so on. In this case, so R is the resource side, but we've already included another variable, which is G, which basically stands for any type of environmental considerations or variables. So it is there a bit as a, if you want to represent other variables of consideration. We'll see later on that this could be linked to either population, for instance, or effort in harvesting. So the best known example for the degradation and regeneration of a resource function is the so-called logistic growth function that you can see here. What it is saying is that this function has to be positive, right? And it has to be, and basically, it is worth 0 when the resource has been depleted and is 0, but it also worth 0 when we reach a certain level, which is the level K, which basically represents the carrying capacity of the resource. So that could be because the there's not enough food available, for instance, for a particular population to keep renewing. There's not enough space and things like that. So the idea is that there's an upper bound constraint on how much the resource can grow. So let's have a look at different types of harvesting functions. So we can start with the so-called resource population coupling, where the consumption and the harvesting function actually comes from a sort of prorated allocation or per capita consumption. So what you see is that the population itself grows. So small b stands for birth, m for mortality, and so the population grows at a rate that's the differential between those two quantities. And at the same time, as we can see, so we recover the regeneration function, but we've got a harvesting function which is fundamentally which depends on the population itself, right? So we would assume that a certain share, let's say beta, goes to every member of the human population. So the model here is deterministic, and so fundamentally the harvest function is just a deterministic drift. But we could start including a lot more things in this model. We could also start including a feedback loop between the population dynamics of the resource and the population dynamics of humans, for instance, so on and so forth. So the second example, which is probably a bit more interesting, is based on strategic economic behavior. And so here we only consider a Cobb-Douglas function just for the sake of simplicity. So in this case, the environmental variable G has been replaced with an effort variable, which we call E. And so the idea is that the harvest function is itself a function of two things. The effort that's produced, let's say by fishermen, for example, and R, which is also the resource that's available, right? So the idea is that epsilon here is a measure of effectiveness, so typically catch per unit of effort, and A and B are just exponents, but they're fundamentally the elasticities of effort and resource, right? And so now the quick question is, actually E is an exogenous variable, and so this really depends, again, let's say on a specific industry, on fishermen, on organization, and many such considerations. And so the idea, one very basic approach to it is profit maximization. So we're going to choose E that's going to maximize a profit. So the profit is going to be, as usual, P times the harvest function. So we suppose that you everything that you harvest, every catch that you get, let's say again from a certain population of fish, you can sell at a price P, while at the same time any effort costs you C per unit of effort. So we end up with this expression for the profit. And then all we have to do is basically solve for it, and we find the optimal effort, and taking this optimal effort in consideration and plugging it back into the harvesting function, we do find that the harvest function, if you want, is up to a constant equal to the resource itself, up to a certain power. So what's really interesting here is that if you go back to the initial calculus function, right, the power was simply b. But if you now look at the impact of strategic behavior, you see that it's b divided by 1 minus a. And so the idea is, because a is strictly between 0 and 1, you can see that b divided by 1 minus a is actually greater than b. So what that means is that the strategic behavior has actually increased, would tend to increase, if you want, the amount of resource that's being captured, right? So so that's a fairly important finding, which is to say that pure economic behavior and pure profit maximization would tend to lead to an increased exploitation of the resource. So let's now move on to a so-called sustainability principle, which is in this particular framework, right? So it's quite specific to resource management. If we recall the dynamics of the particular resource, the idea is we see that a way of maintaining sustainability would be to ensure that the resource is neutral, in the sense that there's the resource population is kept constant. And so another way of ensuring that is to ensure that the first derivative is 0, so that there's no increase or decrease in the population. And what that means also is that the harvest function has to equal to the regeneration functions, which makes sense. We're just sort of saying you can only consume so much of the resource as it renews itself. So going back to the two examples that we chose in the per capita framework and the profit maximization setup, what we find in the first case is that beta is equal to this particular expression. What's interesting about it is, again, it goes to 0 if the resource goes to the carrying capacity, K, but it also decreases with speed, which is, so we've got a view of the world here where the allocation per capita is going to decrease with the population. On the other hand, we've got the profit maximizing setup, and so we find a slightly more complex expression. But what's really important is that the effort also decreases if the resource is close to 0 or the carrying capacity, which is quite important. And the second thing is that if R is fairly small, right, so typically R is a lot less than K, then what we find is that the optimal effort that would come from the sustainability principle is again R to a certain power. And the idea here is that the power itself, the exponent, is quite different from the one we would get in the profit maximization. So here it's a bit of we see, for instance, that if B and A are equal to 1/2, then we get the same answer, but typically those two values will be quite different. And so we can have quite significant imbalances between what would be put forward by the sustainability principle versus what comes from profit maximization. So now let's move on to the second and the last part of the talk, which is really around randomness and uncertainty, right? So the issue here is that in real life, the resources environment is actually stochastic. So there are shocks, there are additional factors that we've not considered. So there are lots of other variables that actually play a role. The second one, and this is more about uncertainty, is to say that the degradation and regeneration function, F, is fundamentally unknown or unobserved or rarely observed, right? And so we do need an approach whereby we capture that uncertainty. So typically we put a prior on that function, and because it is a function, it needs to be a functional prior, not just a parameter. And last but not least, human behaviors are generally quite difficult to observe or assess precisely. And typically the harvest function itself would not be observed, right, as much as the degradation and regeneration function. And finally, the strategic behavior that we've observed is really based on the perceived law of motion. What we mean by that is that players in the sort of game, if there are multiple actors or multiple fishermen or fisheries, the idea would be that they would tend to base their own choices on actually a perceived law of motion as opposed to the real law of motion. And so if there are errors in the way they perceive the resources stock, for instance, then what that means is that there are going to be mistakes made in their own choices based on that. Okay, so a natural way to do that is to actually introduce Gaussian processes. So Gaussian processes are a well-known tool of non-parameter Bayesian modeling. And so the idea is that it puts a prior on function. That's really why it is so useful. In a nutshell, a Gaussian process is a random function with an input that we call xi here. And so this is the same as saying that any finite collection of random variables x, xi1, all the way to x, xin. So we're basically evaluating this random function in n different points as a multidimensional Gaussian distribution. So typically we need to specify mean function. This mean function is generally set to 0 because it's actually not really important in practice. But we have the more important bit, which is the covariance or kernel function, which helps define, if you want, the dependency structure across all those observations. So now that we have this, we can actually move to to the second part and move back to our initial framework, which is if we go back to the dynamics of the resource, R of t. Then what we see is that we can write that as a stochastic differential equation, if you want, where we've added some noise, which is d omega t, and we've also added some uncertainty in alpha t and kt, right? So what this is saying is that in blue is really what's uncertain, and in red is what's random. Well, lo and behold, what's really great with Gaussian processes is that both parts can actually be handled in a very similar way, because Brown motion or Steiner-Langberg processes are themselves Gaussian processes. So this is really neat, and this enables us to have the discretized system that you can see here. And the idea behind that discretized system is that we would typically not observe a resource in continuous time. We would typically only observe it at certain points in time, right? And so we can simulate that. And so all the results are in the paper. But what you can see is that we would usually, with the sustainable principle, we would typically have a constant population of 500, right? Which is the starting point that we've chosen. Instead, we can see that even with very reasonable parameters, we get a fairly large we get fairly large swings in that value, and in particular, we can see that sometimes the actual stock is variable. And so what that means is that if at that point in time the results were not observed perfectly by a number of players, then there could be depletion of the results, even though people were behaving in an actually fairly sustainable way. Finally, you can also see across a number of runs the distribution of the final result side. So we've run it for, let's say, 1,000 days with those parameters, and for every one we look at the value of that results at time 1,000, and we can see that it can be very different. Obviously, it's centered around the initial starting point because we've made sustainable choices, but at the same time, sort of what we call basic sustainability can lead actually to resource depletion if we do not include those dimensions. Right, so this is really the last consideration, which is just to say that usually we would go the reverse, which means that we would observe the resource at certain points in time, and we would have to infer actually how it is evolving. And so this would actually correspond to a filtering problem that would be in the same framework that we've already talked about, which is that of Gaussian process. So all the details are in the paper, but the idea is that we just rewrite slightly the law of motion. We make it local because we don't have access to more information, and based on that, we put a prior, if you want, on the drift that we observe here, which would be again a Gaussian process. Conditioning on the drift, and we're using, for instance, the previous discretized approximation. We know that the resource at time t plus 1, conditional on the previous resource and conditional on the drift, is assessed Gaussian. So this is really Kalman filtering. This is very a well-trodden path, and so we can then estimate the distribution of the drift. And so in this case, for instance, we represented it for a particular path, and what you can see in red is the actual estimate of the drift, and you have it as plus or minus 1 standard deviation. And so what that means is that you can see that because we've simulated additional factors, you can see that sometimes actually the filtering fails to capture all the scope, if you want, of the uncertainty and the randomness. And so this can cause some problems, but this is a fairly good tool because you can see that the filtering actually does track fairly well the core movements that we can see. So last but not least, in conclusion, we can see that strategic behaviors, randomness, and uncertainty are absolutely crucial. We have, if you introduced a framework that is based on Gaussian processes, which we think is a very natural way of tackling those challenges. Lots of additional research ahead, in particular multi-agent modeling, multiple resources, and trying to include the impact of climate change or environmental factors